After learning about solving powers of complex numbers, is the solution for roots just the reverse? Check how this is done here in Mathematics of Engineering. Looking for the root of a complex number in rectangular format has a specific procedure. Say we are to determine the square root of the complex number 3 plus 4i. The answer we are to expect after the operation is a plus bi. So we can write the square root of 3 plus 4i as equal to a plus bi. First is to free the equation from radicals. So take the square of both ends, where the left becomes 3 plus 4i, and the right side of the equation can be expanded as a squared plus 2abi plus bi squared. The last term can be expanded as b squared times I squared, where the last part is taken as -1. Regroup the real numbers and the imaginary. So 3 plus 4i is equated with a squared minus b squared plus the imaginary part 2ab. Now interpret the equation by parts, where a squared minus b squared is equal to 3, and 2ab is 4, where b can be taken as 4 over 2a, or b is 2 over a. Consider the real numbers equation as equation 1, and b as the second equation. Plug the second equation into the first and get a squared minus the square of b, which is now 2 over a, as equal to 3. This is simplified as a squared minus 4 over a squared as equal to 3. Multiply a squared into the equation and get a raised to 4 minus 4 as equal to 3a squared. Let's arrange this into the quadratic equation. A raised to 4 minus 3a squared minus 4 is equal to 0. The expression can be factored as a squared minus 4 times a squared plus 1. So equating them into 0, we get a squared as 4, where we can extract a as positive and negative 2. From the other factor, a squared is then equal to -1, and a is then I. If we let a equal to positive 2, knowing b as 2 over a, b is then computed as 2 over 2, which is 1. So using the format a plus bi, the root of 3 plus 4i is equal to 2 plus 1i, or simply 2 plus I. If we let a as -2, then plug this into b of 2 over a. b then becomes 2 over -2, which makes -1. So the root of 3 plus 4i is equal to -2 minus I. When a is equal to I, with b as 2 over a, it becomes 2 over I. If I over I is multiplied, the expression becomes 2i over I squared, where the denominator is reduced to -1, making b equal to -2i. From the rectangular format a plus bi, we write I plus -2i times I, simplified as I minus 2i squared. So I squared is -1, making everything I plus 2. Thus, the root of 3 plus 4i is equal to 2 plus I. With all answers already determined, we can say that the square root of 3 plus 4i are positive and -2 plus I. Now move on to taking the square root of a complex number in its polar form. Say we work on the square root of 2 times cosine of 4 pi over 3 plus I sine of 4 pi over 3. Using De-Moivre's theorem, we take r as 2. Theta, as 4 pi over 3, and n is 1/2, as this is the rational exponent for square root. So z raised to 1/2 is equal to 2 raised to 1/2 times cosine of 1/2 of 4 pi over 3 plus I sine of 1/2 of 4 pi over 3. So the square root of z is equal to the square root of 2 times cosine of 4 pi over 6 plus I sine of 4 pi over 6. Another example is to take the square root of 5 cosine of 30 degrees plus I sine of 30 degrees. Using the same theorem, we can denote r as 5, theta as 30 degrees, and n as 1/2. So z raised to 1/2 is 5 raised to 1/2 times cosine of half of 30 degrees plus I sine of half of 30 degrees, simplified as the root of z equal to the square root of 5 times cosine of 15 plus I sine of 15 degrees. Using the rational exponent for roots is applicable, although the answer is limited to only the first pair. For the higher roots, the other multiple pairs can be solved by taking the other revolutions. Thus, from De-Moivre's theorem, when theta is in degrees, the formula to use is the nth root of r times cosine of theta plus 360 degrees times k upon n plus I sine of the same quantity. When theta is in radians, the formula is the nth root of r times cosine of theta plus 2 pi times k over n plus I times sine of the same quantity. K is taken as from 0 to n minus 1, which will automatically also give the number of roots. Take note that 360 degrees times k, or 2 pi k, represents one whole revolution. For example, the fourth root of the function 81 cosine of 60 plus I sine of 60 degrees is required. Using the formula, r is 81, theta is 60 degrees, n is 4, so k starts from 0 to 1, 2, and 3. With k as 0, use the long formula, plugging r, theta, n, and k as 0, making the fourth root of 81 times cosine of 60 plus 0 over 4 plus I sine of 60 plus 0 over 4, which simplifies it as 3 times cosine of 60 degrees divided by 4 plus I sine of 60 over 4. So the first root for the complex number is positive and negative 3 cosine of 15 plus I sine of 15 degrees. The second root can be taken as z is equal to 1. This will make the argument one revolution different, so the equation becomes the fourth root of 81 times cosine of 60 plus 360 divided by 4 plus I sine of 60 plus 360 divided by 4. Simplified as 3 times cosine of 420 degrees over 4 plus I sine of 420 degrees divided by 4. So the second root of the numbers positive and negative 3 times cosine of 105 plus I sine of 105 degrees. The third root uses k equal to 2. So plugging this into the formula, we end up with 3 times cosine of 60 plus 720 all over 4 plus I sine of 60 plus 720 over 4. Simplify the argument to have 3 times cosine of 780 degrees over 4 plus I sine of 780 divided by 4. So the third root of the number is positive and negative 3 cosine of 195 plus I sine of 195 degrees. The last pair of roots involve k as 3 in the formula, making it 3 times cosine of 60 plus 1080 over 4 plus I sine of 60 plus 1080 degrees divided by 4. The solution becomes 3 times cosine of 1140 over 4 plus I sine of 1140 degrees over 4, thereby having the fourth roots as positive and negative 3 times cosine of 285 plus I sine of 285 degrees. Another example includes an argument in radians, requiring the fourth root of the complex number 6 cosine of 3 pi over 4 plus I sine of 3 pi all over 4. Check that r is 6, theta is 3 pi over 4, n is 4, and k accounts for 0, 1, 2, and 3. Start with k as 0. The formula becomes the fourth root of 6 times cosine of 3 pi over 4 plus 2 pi k all over 4 plus I sine of 3 pi over 4 plus 2 pi k all over 4, where the whole term involving k is 0. So the reduced form is the fourth root of 6 times cosine of 3 pi over 4 upon 4 plus I sine of the same resulting argument. Then the first pair of roots come from the fourth root of 6 times cosine of 3 pi over 16 plus I sine of 3 pi over 16. Or in decimals, we take positive and negative 1.57 times cosine of 3 pi over 16 plus I sine of 3 pi over 16. With k equal to 1, the formula then turns into the fourth root of 6 times cosine of 3 pi over 4 plus 2 pi, and everything is over 4, plus I sine of the same argument. 2 pi is equal to 8 pi over 4, taking into account the same denominator as theta. So the second pair of roots are from one revolution after, with positive or negative 1.57 times cosine of 11 pi over 16 plus I sine of 11 pi over 16. The next pair of root comes with k equal to 2. With 4 pi taking the same denominator as the argument, it is transformed into 16 pi over 4. So the fourth root of 6 comes as positive and negative 1.57. Then the simplified argument becomes 19 pi over 16. With k equal to 3, the formula with 2 pi k becomes 6 pi. But then we needed to take its equivalent fraction form to be added easily to the argument. So the formula becomes the fourth root of 6 times cosine of 3 pi over 4 plus 24 pi over 4 divided by 4. Then the term with I times sine has the same argument. So adding the arguments, we get 27 pi over 16, resulting to the fourth pair of roots as positive and negative 1.57 times cosine of 27 pi over 16 plus I sine of 27 pi over 16.